For lesson 12.5, for the very first time, you're going to be focused on alternating series exclusively. Now, believe it or not, you would have had a little bit of an introduction to an alternating series already, if you can even believe that. And we'll talk more about that in just a moment. But our learning target is I can use the alternating series test. Let's talk about what an alternating series really is. It's a series whose terms alternate between positive and negative terms. You'll always go from a positive term to a negative and then back to a positive. For example, look at this. 1 minus 1/2 plus 1/3 minus 1/4. You're going from plus, minus, forever. Now, immediately you can think, well, what in the world would sigma look like? What would that formula look like? Well, you can see I've highlighted here in yellow the -1 raised to a power. In this instance, the n-1 power. And granted, we're going to start at n equals 1. -1 to the 1 minus 1, that's -1 to the 0. Hey, we're going to start off with a +1 for our first term's numerator. Down below, we'll just have a 1. And you can see we'll proceed. You know, the kids might look at that and say, gosh, that looks like the harmonic series. Yeah, it's actually the alternating harmonic series. But you can see what's happening. It looks just like an ordinary series, except you've got a positive term and then a negative term. Now, by the way, who's to say that you must start with something positive? Take a look at this second example. You very well could start with something negative. And you will. And you can see you'd go from a -1/2, then to a positive 2/3, then to a negative 3/4. And this will continue on forever. Now, you look at sigma. And you could say, well, now I've got -1 to the n here. And, that means your very first term is -1 to the first power. It's a negative term. That's okay. Alternating series can begin with negative terms. The only main issue is you're going to always change from positive to negative or vice versa. You will always see -1 raised to a power in these series. Always. Now, that being said, you might have noticed I said originally that you've already seen this a little bit. And I do say just a little bit. And if you're really on your toes, you might say, yeah, geometric series. The geometric series. Like, for example, what if we had something like -1/2 to the n? And you could begin to work this out, and you plug in a 1, and you'd say, well, my first term would be -1/2 to the first. That's -1/2. And you'd say plus, well, let n equal 2, and then we'd get, a positive 1/4. And you get the idea. Let n equal 3, and then you'd go to -1/8. And, you're alternating between positive and negative terms. Or starting with a negative and then going to a positive. So you have seen an alternating series before. Maybe you didn't write it out term by term by term, but sometimes these series will converge. With a geometric series, a rare series, we could even tell you what you converge to. Sometimes your series will diverge. So the big question is, how do we know? Guys, what you've been working on the last 3 school days, basic comparison test and limit comparison test, do you think we can use those today? No. Go back to your notes. Everything had to be positive. So all of a sudden you'd say, oh man, I can't use these 2 very important tools that I've been using. You'd say, well, maybe the integral test. No. The integral test was exclusively for positive term series. So all of a sudden, tools at our disposal, all these tests that we have been using, all of a sudden aren't applicable. Guys, you need a new test. And today you're going to get it. The alternating series test. The alternating series test. Here's what it looks like. You will notice, oh, hey, look at that, -1 to a power. It's either -1 to the n, or -1 to the n minus 1, or -1 to the n plus 1. But then you'll get another formula. Most authors are going to call that formula b sub n. And you're going to say, hey, how can I know what's going to happen? Here's what's going to happen. If you satisfy two conditions, notice that the -1 to the n is not included for part A. The -1 to the n is not included here. We're not even looking at it at all. We're just looking at the formula without the -1 raised to a power. And if you can show that b sub n plus 1 is less than or equal to b sub n, that would be sufficient. What that's really saying, if you think about it, oh, your next term, the n plus 1 term, has to be smaller. That's another way of saying that your sequence here is decreasing. Now, you can also take a derivative and show a derivative is negative. But I really want to highlight right here that you can actually do something a little bit different, which might be short. So a derivative is valid if your derivative of a function is negative. But if you can just show b sub n plus 1 is less than or equal to b sub n, that's your first criteria. What's the second criteria? Again, notice for part B, -1 to the n is not thrown in here. It's like we're ignoring it. If you can take your limit as n goes to infinity of b sub n, and if you go to 0, that, guys, is enough. These two conditions, A and B, would say then the series converges. Show those two conditions, and you get convergence for the alternating series. That's officially the alternating series test. So we look at that and we'll say, well, hey, that doesn't seem so bad. I hope it doesn't seem so bad. But notice the 4 stars here, and the fact that I'm also highlighting this. This is probably one of the biggest misconceptions you have to be on guard about. The alternating series test never, ever tells us if a series diverges. It can only tell us if a series will converge. It never tells us if a series diverges. Sometimes kids will say, oh, well, wait, what if part A and B fail? Guys, that just means that the alternating series test won't help us out. Of course, kids are going to ask the next question, well, then what do we do to show divergence? Oh, big question. We're getting to that soon. Okay? But very importantly, the alternating series test can't tell us if a series diverges. Let's jump into our first example, though, and see where we're going. State whether the series converges or diverges. And guys, right now, if you're really on your toes, you're going to say that's the exact problem at the top of the page. It's the alternating harmonic series. The alternating harmonic series. Now, gut instinct, what do you think is going to happen? Do you think this will converge or diverge? What do you think? Almost everybody's going to say, oh, it's got to diverge. Be careful. Alternating series can act very different from their original series that don't alternate. So I understand that everybody, by the way, that's what I would have answered the first time I would have seen it. I'd say my money's on saying this will diverge. Well, let's see if this will even come into play. Here's, I guess, what I want to start off with. You can rewrite this series. You can see I'm kind of doing that. Like this. I'm pulling that -1 to the n minus 1 out in front. Why am I doing that? Because b sub n is just 1 over n. Notice this style. We don't include -1 raised up to a power. We ignore it. That's why I even separated it before I even wrote that down. Your b sub n will never involve -1 up to a power. Now, next kids can think, oh my gosh, Mr. Dobner, that means f of x is 1 over x, and I better show a derivative and show that it's negative, which is not very hard to do, is it? And if you did that, wonderful, that's valid work, it's good. Show that the derivative is negative. You're going to show condition A right above there. You're showing that the b sub n plus 1 is less than or equal to b sub n. Help me out, though. What is b sub n plus 1? What would that literally be? Follow the pattern here. 1 over n plus 1. Think about it. B sub 2 is 1 over 2. B sub 3 is 1 over 3. B sub 4 is 1 over 4. You get the idea. We're not even worrying about positive or negative terms. You'd say, well, b sub n is 1 over n. To find b sub n plus 1, take every n and change it into n plus 1. Now, guys, right now, what's just happened to this new fraction's denominator? It got larger. It got bigger. When a fraction's denominator becomes larger, what happens to the overall value of the fraction? It decreases. It gets smaller. So what you can do is say, right now, b sub n plus 1 is less than or equal to 1, is less than or equal to b sub n. We've checked condition A. I don't even have to take a derivative to do that. I'm showing I know what's happening here. My new fraction is smaller. Okay, so that's kind of cool. It's a bit of a shortcut for you. And then you'd say, well, wait a minute, that's condition A. Yes, here's condition B. I need to take the limit as n goes to infinity of b sub n. And what was b sub n again? Oh, it's 1 over n. And where's that going? 0. That's the second condition. Do you know what that means? We can say by the alternating series test. By the alternating series test, this series converges. This is also going to be used as a statement of fact. This is the most famous alternating series that converges, the alternating harmonic series. Down the road, a couple weeks from now, we'll just be able to use that. We'll say, oh, this is an alternating harmonic series. This must converge. We're going to use it as a statement of fact. Okay? Well, let's jump on over to example 2. And guys, cutting to the chase, tell me what b sub n is here. What's b sub n? 3n all over 4n minus 1. In other words, completely ignore the -1 to a power, which is a good rule of thumb. Now, a lot of times kids get all focused on part A. Dare I say, maybe we should look at part B of the alternating series test. The limit as n goes to infinity. The limit as n goes to infinity of b sub n. Guys, I think you can very quickly use some n behavior and tell me where this limit's headed. Where's it going? 3/4. Uh-oh. It's not 0. I can say at this point that the alternating series test will not help me out here. Right? And that begs the question. You can say, so now what? Well, guys, here's the next question. What if I looked at the -1 to the n minus 1 thrown into this term? I'm looking at this just in general, because remember, the alternating series test won't help me here. I'm going back to 12.2, the nth term test for divergence. when that limit doesn't equal